This slide is based on the lecture notes entirely, and I'm going to show you three matrices. I'm going to show you three row echelon forms, three different row echelon forms, which give you totally different outcomes when you try to back substitute them. First one, all of them taken from the lecture notes. First one is this row echelon form. Look at this. In this row echelon form, we have perfect three pivots. 1, 2, and 3. Perfect three pivots. If you try to back substitute this system, look what happens. Here's a system which corresponds to this row echelon form. Here's the first line, here's the second line, and here's the third line. You see, I'm not going to back substitute right now, but if you do it in your head, just like I imagine you doing the back substitution, you will find exactly one solution. It will be one value for x3 from the line in here. There will be then, when you back substitute x3 in the second line, there will be only one value for x2. When you then back substitute these values into the first equation, there will be exactly one value for x1. Now let's just look in the other row echelon form, this row echelon form. How many pivots we have here? If you just take into account the part of the matrix on the right hand side, what just happened? Then we have 3 pivots. Here's my first two, and here's the third one. It's still a pivot, even though it sits on the right hand side of the bar. It's still a pivot. It matches the requirement of the pivot perfectly. Now, if I give you this system, is a system which corresponds to this row echelon form. That's the system which corresponds to this row echelon form, isn't it? You can't deny that. What we can say about this system? What? In terms of the solutions of the system? No solutions, because the last line is totally like a strange thing. It never happens. 0 never is equal to 7 unless you're in the Z7 finite field, if you remember that discussion. Now, the final example of the row echelon form which explains everything is this row echelon form. How many pivots we have here? This time I will accept your answer. This time we have 2 pivots. Here they are. Here's my 2 pivots, and this is it. This time, if I write the system, if I back substitute my system this time, is a system which corresponds to that. The last equation doesn't make much of a sense. It does make sense, but it doesn't carry any information for us, so we can easily disregard that. But here we observe the non-leading column, and we know how to handle that. We know that this variable, which corresponds to this non-leading column, can be set to any number we wish, and then yet we will be able to solve the rest of it via back substitution. So in this case, we have multiple solutions. In fact, it will be the whole straight line of the solutions. Well, these 3 examples, they are pivotal examples for the row echelon form analysis. And by looking at these examples, I will just generalize them into the theorem, which you're going to use every time you analyze how many solutions system has by looking at the row echelon form. Here's the theorem. Imagine you have an augmented matrix of a system. You see, it's my informal way to write this. So this capital A represents all of the numbers on the left-hand side. This is a vector B, which represents I said the right-hand side. I mean, all on the left-hand side here. The vector B represents the vector on the right-hand side. Imagine by some steps you devised, you converted this into the row echelon form. The theorem will tell you how to judge how many solutions the original system has by looking at the resulting row echelon form. And all of these options are all here. Look at this. Let's just read it together. It's a long sentence. I'm not going to read. let's just see how many options. First one, it says we have no solutions if right-hand side is a leading column. It's this case, you see. When it happened that on the right-hand side we had a pivot, which is the same as to say that the right-hand side is the leading column, when we had such an outcome, the system wasn't solvable. So if you observe that in your row echelon forms, you conclude immediately that the system doesn't have any solutions. Second option says well, let's actually have two sub options. If your right-hand side is not the leading column, then you have two options. Either you will have a unique solution if every column on the left-hand side is the leading one. If every column here is the leading one, in that case, you will have a unique solution. This is the example which was here. Let me just zoom out a little bit. This is the case we observed here. You see, we didn't have the leading column on the right-hand side, but we had all of the columns on the left-hand side. They were leading ones, and that's why we had the unique solution. And the final option is when, let's just see how I put it. We have infinitely many solutions if so many options. At least one column of U is not the leading one. Well, that's expectable final option, which covers the rest of the possibilities.